Okay, so good morning to everyone. Now, in previous class, we have already started about the discussion of the difference between the CISC and RISC. We have started the discussion of it. So again, let's start recap the session that the difference between the CISC and RISC is CISC stands for the complex instruction set computer and RISC stand for the reduced instruction set computer. Now, for CISC, the number of instructions are large. So that means the number of instruction which came into the CISC are in the large number. But whereas for RISC, the number of instructions are less. That means the instructions which came are less in reduced instruction set computer. And for CISC, variable length of instructions. For CISC, the length of the instructions format is variable length. That means it differs that the instruction which came, it may be 16-bit, it may be 32-bit, it may be 64-bit. That means the instruction format is the variable length. That means no fixed length is specified. Some instruction that like a instruction set came and like in the first 3 instruction, it is of 16-bit. Then next 3 instruction, it is of 32-bit. Then next 3 instruction, it is of 64-bit. So variable length instruction format it is. But for RISC, the length of the instruction format is fixed. That means all the instructions which came should be into the same format. That means if a 32-bit instruction came, that means all of the instruction which came are of 32-bit. That means we have said in the variable length instruction for CISC that if total 9, let's say 9 instruction came, and between this 9 instruction, 3 instruction is 16, 3 instruction is 32-bit, then 3 instruction is 64-bit. But for the case of RISC, the whole instruction, that means this 9 instruction which came, should be in the same format. That means if it is 16, then all of the 9 instruction which came out of 16 or 32 or 64. That is the difference between the CISC and RISC. Now, there will be the large number of addressing mode required for CISC. So that, because why it required large number of addressing mode? Because the variable length, we are saying that CISC works on the variable length instruction format. So if the variable length instruction format is there, that means the large number of addressing mode is required. Large number of addressing mode is required for this to construct this variable length, because the variable length instruction come. So that's why the large number of addressing mode is required. But for RISC, it is fixed length instruction. So that means fixed length instruction, and that's why few number of addressing mode is required for the RISC. Then the cost is high. For CISC, the cost is high. Because the cost is high, that's why in CISC, the hardware requirement is much more powerful. That's why if hardware will be the powerful enough, then the cost will be increased. But for RISC, we didn't require so much hardware. We didn't require so much powerful hardware, and that's why the cost is low for RISC. In CISC, several cycle instructions is required, but for RISC, it is the single cycle instruction, and we try to make the CPI that is equal to 1. We will discuss today about the pipelining concept. So in this pipelining concept, there is a concept present, clock per instruction. That means per clock, how many instruction is executed. We always try that in per clock, one instruction is executed. One instruction is executed. We always try to achieve that, but it is not practically possible. That's why we have said that CPI that is equal to, we are trying to equal to 1. But didn't you see that we didn't specify CPI equal to 1, tends to 1. We have specified tends to 1 because we always try that the clock per instruction becomes 1. But practically it is not possible that in each clock pulse a instruction get executed. It is not possible. So that's why we always say that CPI tends to 1. We try that CPI will tends to 1. Then for CISC, manipulation directly in the memory. That means all the operations of the instructions are performed into the memory. But for RISC, only our registers is required. Our registers is required in the RISC. Then micro program control unit based. Our CISC is the micro program control unit based, whereas our RISC is hardware control unit based. Our RISC is the hardware control unit based. Now, through an example, we understand that why we say that CISC and RISC. So some CISC, some examples, these types of computers use the complex instruction set computer, and this type of computers use that the mainframes, then Motorola 6800, Intel 8080, this type of, they use the instructions format of the CISC. And for RISC, the examples are MTS, ARM, Spark, Fugaku, like this. Now this is the example Fugaku. This is the example that in 2020, this is the supercomputer. The supercomputer uses this Fugaku. This is the supercomputer that use the reduced instruction set computer. reduce instruction set. Now, what is the difference? Main difference through an example we understand that here you see mult 2:2. Now, this is our RAM. This is the example. This is in the RAM and this is our registers. So in CISC, how instructions we execute? Let's say we have written instruction mult 2:2 and 3:3. Now, if we see, this is our RAM, and in this RAM, we have, let's say, 4 columns and 4 rows. In this RAM, let's take an example. We have 4 rows and 4 column. Then what is the instruction we written? Mult 2:2 and 3:3. That means in this 2:2, in here, X is stored. In this here, 2:2, here X is stored, and 3:3. In this 3:3, our Y is stored. So whenever we will write this instruction mult 2:2, 3:3, that means what? 2:2, our what value is present in 2:2? X. So X will come, and in 3:3, what value is present in 3:3? Y value is present there. So that's why Y came. So that means we want to directly multiply X into Y, because in 2:2 location, whatever the value is stored, with this we want to multiply the value that is stored into the 3:3 location. The value that is stored into the 3:3 location, 3:3. So in 2:2, X is stored, and 3:3, Y is stored. So we will multiply that both value, and after multiplying this both value, we will store where? In the X location. Because if there is nothing mentioned, that means it is working like an accumulator. So after multiplication between X and Y, where will you store the value? We will store the value again into the X. That means the final product between X, after multiplying X into Y, it will be stored into the X. That means where? That means into the memory location. Now X is where? X is specified in the 2:2 memory location. That means in this 2:2 memory location, the final product will again be stored. So this is what our complex instruction set computer works like this, that in here the instructions executed like this. But for RISC, there is some difference, because we already said that it is work on the register. So that means first what we have to do, we have to transfer that value from memory to the register. That's why you see load A, 2:2. That means the value that is stored into 2:2 location will be transferred to the register A, because in RISC, reduced instruction set computer, it works on the register. Already in our difference, we have already said that it works on the register. That means in this 2:2 location, whatever the value is stored, first it has to be moved to a register. So let's say we have taken RA, that means A register we have taken. So in this location, whatever the value stored, it is transferred to the our register A. That's why first load A, 2:2 is specified. Then same as that, Y has to be also the Y value that is stored into the 3:3 location. It has to be transferred to the register, another register. So that's why we have seen that 3:3 location. In 3:3 location, the value that is stored is transferred to the register B. This is what? This is another register. So that means Y value will be transferred to the B register. After that, what we will do? We will product A, B. So that means now in A and B location, the value is already stored. So in A register and B register, the value is stored now. So after that, what we have to do? we have to do the product between A and B. So after doing the product in the execution unit, there will be an execution unit. In this execution unit, the value that is stored into the register A and the value that is stored into the register B, between them we will do the product. And after that, after the final result we get, now we have to transfer this final result again into the memory, because we have done this total thing into our register. So that means after the final product, the value should be transferred into the RAM again. So that means what? That means after the final product we get, and where we will store, we will see that if this is between this multiplied, and if nothing is specified, that means we have to store into the accumulator. So that means in the register A, the register A will work like an accumulator. Register A will be work like an accumulator here. So that means what? That means the final product we will store into the register A. Then from register A, we will transfer to the memory again. So that's why you see stored. That means in this A, now the final product is present. So this final product will be transferred into the 2:2 location. Now you can say why this 2:2 location? Because this 2:2 location is of X and we are performing X into Y. And we have already said that if after final product in the X, in X, the value will be stored. So that means after doing the operation, it will again stored into the X location. Now X location is present in the memory in which part? It is present in the 2:2 location. That means the final value will be stored into the 2:2 location into the RAM. So that's why this is the command store 2:2 comma A. That means from the final value it will go to the 2:2 location. Okay, so this is the difference. You see here we are directly performing, but here we have to convert it first from memory to register, and then after doing the operation we have to transfer that again into the memory location or our in the RAM in where it was previously stored. So this is the basic difference between the RISC and CISC. Okay, it is clear to everyone?
Yes, sir.
Okay, so this is the difference. Now
Sir.
today we will, हाँ बोलो
सर हम लोग ए एंड बी का प्रोडक्ट को स्टोर करेंगे ना?
हाँ ए एंड बी का प्रोडक्ट. अब देखो ए में क्या था, मेरा एक्स था और बी में वाई था, तो इन दोनों का जो हम लोग मल्टीप्लीकेशन किए, अब उसको क्या है हम लोग जानते हैं कि एक्यूमुलेटर में स्टोर करते हैं. तब अब एक्यूमुलेटर होके कौन सा काम करेगा, क्योंकि हम जानते हैं अगर कुछ मेंशन नहीं रहते हैं तो हम लोग उसको एक्यूमुलेटर में स्टोर करते हैं. तो ये जो है मेरा वो अभी एज ए एक्यूमुलेटर काम करेगा. अब एक्यूमुलेटर क्या है, एक्यूमुलेटर में वैल्यू स्टोर हुआ, मतलब ए जो है ए क्या है मेरा रजिस्टर ए है, तो रजिस्टर ए में मेरा वैल्यू आया, तो रजिस्टर ए में वैल्यू आने के बाद क्या है हमको उसको फिर मेमोरी में ट्रांसफर करना होगा. अब मेमोरी में एज ए एक्यूमुलेटर कौन काम करेगा, 2:2 लोकेशन, क्योंकि उधर ही मेरा एक्स का वैल्यू था, तो वो एज ए मेमोरी लोकेशन जो है वो एज ए एक्यूमुलेटर काम करेगा. तो हम लोग वैल्यू जो है उसको फिर उस 2:2 लोकेशन में लेके जाएंगे. ठीक है?
यस सर, क्लियर.
ओके, सो दिस इज आवर RISC and CISC and difference between CISC and RISC. Now today we will start another topic, that is the concept of computer architecture, that is the pipelining. Now to execute an instruction, it requires 5 stages. In some book you will see 4 stages it is given, so maybe 5 stages or 4 stages. In some books you will get that they are mentioned in 4 stages, but that is also not wrong, but we are considering that 5 stages. So what is this 5 stages? Now if a instruction came, then the instruction, at first this instruction should be fetched. At first that instruction should be fetched. Then after fetching the instruction, that instruction should be decoded. That instruction should be decoded. Now why decoding is done? To know which operations has to be performed and over which operand. This is the instruction decoding. So that means first stage is what? First the instructions will be fetched, then instructions will be decoded. Now why we decode? To know that between in our operand which operations has to be performed and between which operand. This is the instruction decode. Now after that, this instructions should be executed. This instructions should be executed. Now performing the execution of these instructions, after we have to, if memory is required, then after that the memory will be given, and after whole operations are performed, we will store the final result back again into the memory. That means write back. WB is the write back. So after that, the write back means what? The final result will be write back again into the memory. So this is the 5 stages and instructions is executed. Now, let's say we have total, our program is there, and in this program, 8 instructions is present. Now from instructions 1 to instruction 8, total 8 instructions is present in our program. Now that means what? Our processor has to be processed this instruction. Now in non-pipelining, what is that? Let's say we have total 8 instruction in our program. Now non-pipelining is what? In non-pipelining, so to execute, we already know that to execute an instruction we require 5 stages, and we assume that for executing each stage it requires 1 clock cycle. 1 clock cycle it requires. That means 5 stages. We have 5 stages and each stage require 1 clock cycle. So that means total clock cycle will be what? 5 into 1, that means 5. To execute this 5 stage, we require 5 clock cycle. That means what? Let's say we are saying that I1, our first instruction. This I1 is what? To execute this I1 instruction, how many clock cycle will be required? We have total 5 stages and each stage require 1 clock cycle. That means total 5 clock cycle. So that means to execute instruction 1, we require total 5 clock cycle. Same as that for I2 instruction, for to execute this I2 instruction, we will require again 5 clock cycle. Same as that for I3 also, I4 also, I5 also, I6 also, I7 also, and I8 also. That means each instruction, to execute each instruction, we require 5 clock cycle. So total number of instruction, how many instruction is there? 8 instruction is there. To execute total, how many clock cycle will be required? If each instruction required to execute 5 clock cycle, in 5 clock cycle it execute. That means 8 instructions will be executed with how many clock cycle? 5 into 8. That means total 40 clock cycle is required. So total how many clock cycle will be required? 40 clock cycle to perform or execution of this total program. But in non-pipelining architecture, why we do that? Because we want that in number of clock cycle will be less, and in this number of clock cycle less, we execute our total program. Because you see, if we use the non-pipelining architecture, in this non-pipelining architecture, to execute this program, it requires 40 clock cycle. But we want that this total program will be executed in our number of clock cycle will be there less. So in less clock cycle can we perform the execution of this total program? Pipelining architecture give that opportunity. So let's see the diagram. This is the stage versus time diagram. This is the stage versus time diagram. Now, how many stages are there? Total 5 stages are there. So we have said that instruction fetch is S1, instruction fetch is S1, then instruction decode is S2, then execution is S3, memory is S4, and write back is S5. So this is the 5 stage. So this in this y coordinate, what we do, this is S1, S2, S3, S4, S5 we mentioned. The total 5 stages. And here, this is the time. So here, this X coordinate, we mention the time. This is the stage versus time diagram. Now, let's say the first instruction came. The first instruction is I1. Now, I1 came at first clock cycle. Now, when the first clock cycle I1 came, it will do what? It will fetch the instruction first. So instruction fetch will be done into the I1 stage. Into the I1 stage, the instruction 1 will do what? Instruction 1 will stage in the stage 1, that means I1 instruction in the instruction fetch. It will do the instruction fetch there in the first clock cycle. Now, next in the I2. Now, next, when after fetching the instruction, I1 will do what? I1 will do instruction decode. Now, I1 goes here in the S2. Now, S2 is what? S2 is our instruction decode. So, in the next clock cycle, I1 do what? In the next clock cycle, that is 2, second clock cycle, I1 started instruction decode. Now, if I see I1 is doing the instruction decode, but that time instruction fetch stage is ideal. So can we give the opportunity for the next instruction to use that stage? That is the difference. In this second clock cycle, I2, our next instruction, will started instruction fetch. Okay. So after that, in the third clock cycle, instruction 1 goes where? Instruction 1 goes in the execution stage. Now our instruction decode and instruction fetch are ideal. So that means instruction 2, our next instruction, in that time will use the instruction decode stage, and instruction fetch is ideal. So instruction fetch is ideal. So in that time, the next instruction I3 will start at the instruction fetch. So after that, in the fourth clock cycle, our next instruction in the fourth clock cycle is what? This is the our I1. So I1 in this fourth clock cycle goes to the memory stage, and instruction 2 started executing in that clock cycle, and instruction 3 is started decoding. That means it is starting instruction decode. And our next instruction, that is the instruction 4, that started what? That started the instruction fetch. Same as that, after that I1, so it goes to the memory. Till now it goes to the memory, and after that I1 instruction in the fifth clock cycle, it do the write back. And I2 instruction is using the memory now. Then I3 instruction is using the execution stage now. I4 instruction is using the instruction decode stage now, and I5 instruction is using the instruction fetch now. So that means in this fifth clock cycle, you see each total 5 instruction. This total 5 instructions are now present. That means instruction in each stage, one instruction is present. In write back stage, I1 present. In memory, I2 present. In execution stage, I3 present. In instruction decode stage, I4 present. And in instruction fetch stage, I5 is present. So that is the difference. If we use the non-pipelining architecture, in that time, that means till fifth clock cycle, only I1 should be executed and no other instruction is not in the frame. That means after completing the I1 instruction, then I2 instruction started the from stage 1, then stage 2, then stage 3. So that means after 5, you see after 5 clock pulse, the instruction 1 get execute. The instruction 1 get executed. Then in next clock cycle, I2 will go there. I2 will go to the write back stage. So that means in the next clock cycle, I2 will be executed. Then in the next clock cycle, I3 will be executed. Then in next clock cycle, I4 executed. So that means what? That means in each clock cycle, you see the first, after you see that the first instruction required the 5 clock cycle. But after that, in each and every clock cycle, you see an instruction is executed. An instruction get executed after the first clock cycle get execution. So this is the difference. This is the basic difference. Then if we done it into the our non-pipelining architecture, that means I1 get 5 clock cycle to execute. I2 will require 10 clock cycle to execute. I3 will require 15 clock cycle to execute. But here you see I1 get 5 clock cycle for execution. I2 will go for execution 6 clock cycle. So that means in each clock cycle, a instruction get executed. That is the difference. That is why we use the pipelining architecture. And now the difference, we have said that CPI, the CPI that is tends to, we have said that is tends to 1 clock per instruction, because we always want that in each clock cycle a instruction get executed. You see, only the first instruction required 5 clock cycle, but after that in each clock cycle a instruction came out for execution, came out after the execution. So this is the pipelining concept. This is what. So if let's say if we take our total instruction is n, and if we say our number of stages is k, our number of stages k, that means if we have total, our instruction is n, and the number of stages, what? The number of stages k. That means for execution of the first instruction, For execution of the first instruction, here 5 stages are present, so that's why 5 clock cycle is required. So that means the for first execution, here the number of stages is what? K. So that means for execution of the first, first instruction, it require what? Number of stages. So that means our here the number of stages is K. So that means for execution first instruction, it require K clock cycle. And other than first, each and every instruction get executed in 1 clock cycle. So that's why n minus 1 into 1, because the first instruction require number of clock cycle is equal to the number of stages. So that means here 5 stage present, so 5 clock cycle required. So that number of stages is K. So we are considering K here, because it will require K clock cycle. And other than the first instruction, we see that next instruction 6, third instruction 7. So that means other than the first instruction, all the instruction get executed into 1 clock cycle. So that's why our total it will become K plus n minus 1 into K plus n minus 1. So now if we take this, our 5 stages is present. So 5 plus number of instruction is what? Number of total 8 instruction is present. So if we see 8 minus 1, that this will become, you see, 12 now. This will become 12. So see, in 12 clock cycle, this total program get executed. But whereas we have seen that if we use the non-pipelining architecture, then we require what? Then we require total 40 clock cycle to execute this whole program. So you see, in the non-pipelining, we require much more clock cycle. But in pipelining, in this number of clock cycle is less, and here in this number of clock cycle less, we have done the total program, we have executed it. Okay, clear to everyone?
Yes, sir.
Okay, so this is the concept of the pipelining. But normally, in theoretically, it is possible that we want in each clock cycle a instruction get executed, but practically it is not possible. Now, why this are not possible? This is not possible because of some hazards. Hazards means the problem. Because of some problem, it always not the thing that in each clock cycle an instruction will get executed. Because let's say I1 get executed, and after that the I2, the next instruction, it has some complex operation present in that, so it may require much more time. Let's say, because in practically it happened that some instruction is very much simple, some instruction is complex. So that's why what problem will be occur, that let's say instruction 1 is very simple and it executed, but instruction 2, in instruction 2 our total the instruction is very much complex. So that means for execution it require much more time. Then so that means what, some clock cycle it become ideal, and after that the result is shown. So it is not possible that in each clock cycle the result we will see. This is, that's why we say CPI tends to 1. That means we always try that tends to 1, but it is not equal to 1. Okay, so this is what our pipelining, and